Hello, everybody. Okay, as promised, there's a few other decisions that you need to make with your telescope to get the data that you need, get the images that you want, to pick the right tool for the right job, right? And that is how you mount the telescope and what detector you're going to put on the telescope, all right? Like I said in the video lecture, what is a mount, right? A mount is basically the infrastructure that you use to stand up the telescope and move it, how you point and move the telescope. So an Altaz mount, right, is like this, right? An Altaz mount is like a cannon where the telescope can move up and down and turn around, which is to say it can move up and down to look high and low in the sky in altitude, and it can turn around to look around the horizon in azimuth, right? Or you can tilt the telescope so that the telescope lines up with, so that the rotation axis of the telescope lines up with the North Celestial Pole. And so if your telescope is aligned to the North Pole, then when you move the telescope left or right, you're going to move it east or west. And if you move the telescope up and down, then it'll move in north and south. So by mounting the telescope equatorially, the telescope can move in right ascension and declination. Right? Right. What are the pros and cons? Right? What are the advantages and disadvantages? What are your considerations when you're picking the right tool? Well, an Altaz mount is easier, right? You don't have to align it with the North Celestial Pole. Right? Mounting a telescope equatorially, you gotta, right? Like this is just easy, right? It's like a cannon. You just tilt the telescope up and down, turn it left or right, piece of cake. An equatorial mount, you gotta tilt the telescope at an angle. You gotta make sure that it's tilted so that it's lined up perfectly with the North Celestial Pole. It's a lot of work, and so it's extra equipment. It takes a lot of work for calibrating. Altaz mount, what's the advantage? It's cheaper and easier. Equatorial mount, the equatorial mount's disadvantage is it's more expensive, and it requires more calibrating and setting up. What's the disadvantage of an Altaz mount? An Altaz mount can't track an object all night long, because how does everything move over the course of the night? Objects rise in the east, cross the sky, set in the west, right? The stars and everything in the sky is moving east to west. Well, an Altaz mount doesn't move east to west. It moves up and down, left and right. An equatorial mount, because the telescope is tilted to align with the North Celestial Pole, then the telescope can rotate itself and it'll move east to west just like the sky does. So an equatorial mount can track. So, what's the advantage? Cheap. Expensive. An equatorial mount can track an object all night long. An Altaz mount can't track objects over the course of the night. Right? So if you're wanting to watch an object all night long, you got to track it. So you got to put in the work and the money to mount your telescope equatorially. If you just want to point your telescope and take a quick snapshot and then you're done, then you don't need to track it all night long. So use an Altaz mount. Why not? Okay. How about detectors? Right? We've got these four main kinds of detectors. What are the properties? Well, let's do this the other way around, right? Which of these detectors will take a permanent image and can measure the colors of objects if you have a filter set attached to it? That's a camera, right? You're taking a picture. You're taking a permanent image that's a camera, right? And like I said in the video, a CCD camera just by itself is black and white. But if you attach filters, right? Take a picture of the sky in the red light, take a picture in the green light, take a picture in the blue light, and then you layer those three colors together, and you can create a picture that is true to the human eye, right? Just the CCD camera, it's going to be black and white. With filters, you can take a color picture. Which of these detectors measures things like composition, what something's made of, what its temperature is, how fast it's moving? That's what a spectrometer is for. For reasons that we will get into. I didn't want to throw this at you all at once. So in a few days, we will get into, all right, what does a spectrometer do? And how does attaching a spectrometer to a telescope help you figure out temperature and velocity and composition and all that kinds of stuff? We'll get there. But suffice to say, a spectrometer does not take a picture. It doesn't take an image like a camera does. It measures the light differently to figure out things like temperature. Right? Which of these measures the brightness and changes in brightness really easily? That's what a timing device is. Right? A timing device is just a quick and dirty camera that takes a quick snapshot, takes a quick look at a star or whatever you're looking at and measures how bright it is. Right? It doesn't care about taking a picture. All it cares about is how bright the thing is, and then making multiple measurements of brightness over and over and over and over and over, so that you can see how the brightness of something changes over time, which is why it's called a timing device. Right? Which of these things is free and available, but can't take a permanent image? Well, that's your eye, right? You already come with those. All right. So let's put this all together with what we were doing last time, right? Let's think about what are these other choices? What would you use? What kind of mount would you use if you wanted to take a photograph of a comet? Well, a comet is, pretty faint, right? A comet is faint, especially like the wispy tail of a comet. That's faint. You're going to want to take a long exposure image. You're going to want to soak up light for a while so that you can see all of those faint details. So if you're going to want to look at that comet for a long period of time and take a long exposure image, you want to track it. You're not just taking a quick snapshot. You're going to take an image for several minutes maybe. In which case you need to track. So you're going to use an equatorial mount to track that comet. Suppose you just want to go in your backyard, do some stargazing, right? Move your telescope around and see what you can see. Well, then you don't need to spend the time and money tracking. You're just going to point your telescope and show your little brother or sister, what you can see. Then use an Altaz mount. Couldn't be easier. Okay? Suppose you don't have much money. Then save your money on an Altaz mount, right? Don't spend the extra money on an Altaz mount. Save that money and use it to get a bigger telescope. Because, a bigger telescope is better, right? Bigger means you've got a larger diameter, you can see fainter things, and you can see them with higher resolution and all that. So, pick the right tool for the right job. And, economics is a factor in science. And so since we don't have, since none of us has unlimited amounts of money to spend on telescopes, you got to make compromises and say, well, do I really need an equatorial mount? Because if I really don't need it, I can save some money and just do an Altaz. All right. If you want to take a photograph of a comet, which of these detectors takes a photograph? That's the CCD, because a CCD is a camera. What if you want to measure the color? Well, we can see color in our eyes, right? Our eyes can see color. Can you measure the color, though? Not very well. Right? Our eyes can see color. Oh, that star is blue. That star is red, etc. It's not doing a great job actually measuring how blue, how red. A CCD, though, can measure the color of something if it has a filter set. So if you're wanting to do a really good measurement and you've got filters to attach to your camera, then use the CCD camera. Yeah. The problem with, again, we're saying like, well, why not just save the money? Use your eye. Your eye's free. In order for our eyes to see color, you need a lot of light, right? The cells in our eye, the cone cells in our eye that can perceive color, they need a lot of light to stimulate them in order to see color. And so if you've got a really bright red star, if it's bright enough, you'll see it's red. If it's really bright and blue, it'll look blue to you. But let's be honest. You go out in your backyard and you look at the stars. Most of the stars in the sky are not bright enough for you to clearly see color. They're not stimulating your eye enough with light for your eye to pick out different colors. They all just look white, essentially. And so the other problem with, seeing color with your eye is that it only works for the very brightest things. Whereas if you've got a CCD camera and the set of color filters, you can measure the color for any star. The bright ones, the faint ones, all of them. Number 3. You want to measure how the brightness of a star changes when a planet moves in front of it. Well, which of these devices measures changes in brightness over time? That's your timing device. Which of them would you use to determine the composition of a star? That's your spectroscope. Or in the previous page, I called it a spectrometer. Same thing, right? The spectrum, the spectroscope, that's what can tell composition, temperature, velocity, all that good stuff. All right, let's put this together. You want to take a picture of a faint galaxy to make an advertising poster for a science fiction movie. So you're doing the graphic design to make a poster for a sci-fi movie, and you need a pretty picture of a galaxy for your poster. All right. You're wanting to take a picture. Which of these detectors takes a picture? The camera, right? The CCD camera. Great. It's faint, though, right? If that galaxy is faint, you're going to want to take a long exposure. You're going to want to take your camera and point that camera at the galaxy and let the camera soak up light for a long period of time. And if you want to watch that galaxy for a long period of time, you need to track. You need to track that galaxy as it goes across the sky. And if you're going to track it, you need an equatorial mount. Right? Take your telescope, point at the galaxy, turn on the clock drive so that the telescope moves with the galaxy all night long, and you can soak up the light in your camera, and then by the time you download the image off the camera, it'll look nice and bright. And hopefully pretty and in color for your poster. So there you go. All right? Said it before and I'll say it again, right? It's all about starting from the end. I need to do this, so I need to make what decisions? About a refracting telescope or a reflecting telescope. Short focal length or long focal length. What kind of mount? What kind of detector? After you've made those 4 decisions, you're ready to go. You know that it'll take the image that you need to do what you want to do with it. Either, measure the composition of the star, or track its changes in brightness, or just take a pretty picture for a poster. Because you've made those decisions, you know you're going to get the picture you want. So you're ready to go. All right. The practice, the microtest practice has some similar questions, so go ahead and knock those out, and then after that you're ready for the placing telescopes Taurus lesson. So go on with that, and if you got some questions, send them to me. All right, have a good one, everybody.